Hi all, in this video we are going to see the mathematical foundation of logistic regression to solve the binary classification problems. And to start with, logistic regression comes under the category of supervised learning in order to solve the classification problems. So logistic regression mainly used to predict the dependent variables based on the independent variables, and here our target outcome is the categorical variable, which is a label. Either it can be a 0 or 1 because it is mainly used for the identifying the binary classification, and also it is based on the concept of the probability. So here we see some of the examples of the binary classification problem, that is predicting the email is a spam or not. And not only these applications limited, we have the diverse application domain which you can use these logistic regression. And now we all know about the linear regression. Linear regression are mainly used to predict a dependent variable based on the independent variable. And here the organization wants to determine an employee's salary, and this is a dependent variable based on the employee rating, which is an independent variable. And for this purpose, we try to draw a linear regression algorithm. So it will predict a continuous value. So by using an equation called as y is equal to a0 plus a1x, and where a0 and a1 are called as regression coefficient, which will be learned from the input data. And here we can see that when the employee rating increases, the salary increases based on the independent variable. That is, here the salary is a dependent variable and the rating is the independent variable. And now, can we use the linear regression to perform a binary classification task? It's not. Okay. So why the linear regression is not suitable for the classification? So there are three different problems when we use the linear regression to solve the classification problem. The first one, we all know that linear regression produces the output as a continuous variable, which is not a discrete, but the classification needs a value which can be either 0 or 1, but the continuous value will produce the values from minus infinity to infinity. So we have to define a threshold, and you need to tell whatever values below the threshold will be going to a class 0 and greater than the value will be going to the class 1. And the next one is the linear regression having a problem of poor handling of the clear boundaries, because these lines not guarantee the output within the range. So when we draw a linear line, it can be vary from minus infinity to infinity. But our classification needs a range only with the values from 0 to 1. And the third problem is it is not robust to outlier. Since we are using the minimization of mean square error for minimizing the cost function in the linear regression, which is very much sensitive to the outlier and the noise. These outliers will normally shift the boundaries of your decision. So now consider this is your problem. We have a tumor size. So based on the tumor size, we need to identify whether the particular tumor is a malignant or not. Suppose you are giving this problem to a linear regression. So now what happens when you draw a linear line? We are not able to identify whether the class is 0 or 1, since you have your data which is restricted to 1 and 0 as a class label. But the linear regression line produces a continuous output which can be varies from minus infinity to infinity. So what we can do is we can define a particular threshold, that may be some threshold value. So whatever value that belongs, that is less than the threshold, here you can specify a threshold is based on a tumor size. So if a particular tumor is below this threshold tumor size, it will not be malignant. If it is above the threshold, it will be malignant. So you can define some threshold and you can make it a linear regression to be act as a classification. But there may be some situation that there may be some noises are introduced. Okay, so when the noise is introduced, your decision boundary get shifted. So the threshold value, whatever we define, is moved now here based on the linear regression line. So in this case, even though these are the tumors which are malignant, now these are identified as non-malignant. So this is the main problem why we are not using the linear regression for the classification. So as I already told, you can have a linear regression line. So we draw a line. So based on the threshold value, whatever value come less than that, that will be one class, that will be going above that will be another class. So these values will be varying from minus infinity to infinity. But our classification problem needs the output is either 1 or 0. So we want to skew your line between 0 to 1. So our output should be like this, but we don't have any line which represent these type of line representation. So what we are going to do is we are using a sigmoid function, that is nothing but S curve or sigmoid function. So what it makes, it will skew your output to 0 to 1 with the probability values. So now we define any threshold. So it makes the values less than the threshold will move to the class 0, greater than the threshold will go to the class 1. So this sigmoid function will be defined by the equation, that is sigma x is equal to 1 by 1 plus e power minus x. So this will be a threshold. The values whatever you are getting out of the sigmoid will be varies from 0 to 1. Okay. So you have a value above the threshold will be going to the class 1, or below the threshold will be going to the class 0. So now you can just check with the problem. You want to give a promotion to an employee based on his performance. So whether the employee is provided with a promotion or not. So now, as I told, you have a linear line that can be extended to minus infinity to infinity. So now you want to skew your line to represent, it can be either 1 or 0. So to make it to this, we don't have any representation to represent this line representation. That's why we are making a line to a S-curve or a sigmoid function. So this is the equation for the sigmoid function. So it will provide all values with the probability value between 0 to 1. And logistic regression actually derived from the linear equation only. But the linear equation generally provides the values of output as minus infinity to infinity. But the logistic regression needs the categorical variable only with 0 and 1. So what we are going to do is the predicted values will be now mapped to the probabilities using the sigmoid function. So your output will be squeezed in the range of 0 to 1. So the straight line will be now viewed as a S-curve or the sigmoid curve to support the probability for the logistic regression to perform the binary classification operation. And now I will go the theoretical background or the mathematical formulation, how the linear regression is formed as a sigmoid function to make us a binary classification. So as you all know that the linear equation starts with y is equal to b0 plus b1x. So this is our linear equation, and this will provide the output as a continuous value which can be minus infinity to plus infinity. But you know that the logistic regression, you need your outputs that should be a probability value, and that should be in the range of 0 to 1. Okay. So to derive this, we are using a probability concept called as odds probability. So what is meant by odds probability? Odds probability means it provides measure of likelihood of a particular outcome. Okay, so this will be represented with the equation odds is equal to outcome that occurred divided by outcome that does not occur. Okay, so this is the formula for the odds. So as you know, the probability of any two events. So this is an event occur, this is an event not occur. So the probability will be going to 1. So this I am going to represent the outcome occurred is y. The outcome not occurred is 1 minus y. Okay. So if I put y is equal to 0, then the output I get is, the odds I get is 0. So if I put y is equal to 1, the odds outcome I get is infinity. So this odds probability now makes your linear regression output. Your linear regression is 0 to, the linear regression is minus infinity to infinity. Now using the odds probability, this will be now reduced to a range of 0 to infinity. But the logistic regression wants the output is 0 to 1. So to make the output of logistic regression to 0 to 1, what we have to do? You have to take a log. Okay. So when you take a log, you need to take a log of log y divided by 1 minus y. So this function is called as logit function. And now the equation is formed like this. As you know, the linear equation is y is equal to b0 plus b1x. This y now I change to logit function. So the logit function is 1 minus y. That's equal to our equation b0 plus b1x. So now we want to solve the y. So to solve y, what we have to do? We have to take exponent on both sides. Exponent on both sides. So if you take an exponent, it becomes y 1 minus y is equal to e power b0 plus b1x. So when you cross multiply, you get y is equal to 1 minus y e power b0 plus b1x. So what we have to do is, again you need to multiply this inside it. So e power b0 plus b1x minus y into e power b0 plus b1x. So you change every y to the left side. So y plus y e power b0 plus b1x is equal to e power b0 plus b1x. Okay, so now you make y should be come outside. So make y should be, take y as a common. So 1 plus e power b0 plus b1x, which is equal to e power b0 plus b1x. So this you make solving y, since you need y. So y is equal to 1 minus, that is y is equal to e power b0 plus b1x divided by 1 plus e power b0 plus b1x. So to simplify this, what I am going to do is, I am making this numerator to the denominator. So e power minus b0 plus b1x plus 1 plus, it's not plus, it is a multiplication of 1 plus e power b0 plus b1x. So now it is multiplied inside. So you got e power minus b0 plus b1x. When you multiply this to this, you have e power 0, e power 0 is 1. So you got everything 1 divided by this. So this can be written as 1 divided by 1 plus e power minus b naught plus b1x. So now our y get solved. Okay. So this how you can write it? You can write as this is actually a sigmoid function. Sigma of x is equal to 1 by 1 plus e power minus x. The same format only we got it here. So sigma of y is equal to, we are getting with 1 by 1 plus e power minus b naught plus b1x. Initially we have y is equal to b naught plus b1x. That is our linear equation. Now it is changed to a sigmoid function to solve the logistic regression. So we all know that when you have with y is equal to wx plus b, we have applying a sigmoid function to it. When you apply sigmoid function, you have the predicted value. This is our actual value and this is our predicted value. And now we find the difference. Difference is the error which can be actual minus predicted. So when your predicted value is greater than or equal to a threshold, it belongs to class 1. When the predicted value is less than the threshold, and it becomes the another class. Okay. So this is the way how we are getting the sigmoid function which is used to solve a binary classification problem for the logistic regression, which is derived actually from our linear regression. And now the cast function. So the cast function for the linear regression. Cast function for linear regression is MSE. So actually we need to minimize the MSE for the cast function of the linear regression, but the same cast function will not be used for logistic regression because it is stuck into a local optimal problem. So what is mean by local optimal problem? So which is nothing but maybe this is my global minimum. Okay, this is a cast function projected and this is my global minimum. So what happens when the algorithm runs? It finds something minimum here. So this is actually a local minimum, but this is my global minimum for the particular problem to be solved. But when the algorithm finds this the cast area which have a local minimum, it gets stuck into it. So it will not able to reach the actual global minimum. That's why we are not using the MSE as a cast function for the logistic regression. Not for logistic regression. So then what is the cast function for the logistic regression? This is the cast function for the logistic regression. So how it will work? So I will show with one example. So when you see a case 1, so the case 1, our actual value is 1. Okay. So when you substitute y equal to 1 here, this term becomes 0. Maybe you consider this is term 1, term 2. So the term 2 becomes 0. So you will get the cast value is log y predicted. So the predicted value can be a 0, can be a 1. So now the y can be 1. So based on this log y predicted, the y predicted value can be 0. So when you take log of 0, so what will be the log of 0? So log of 0 is the infinity. So you will get the large error. So you can see here, this is y equal to 1. Our y predicted value is 0. This is a threshold function. It specifies the predicted value is 0. So when the predicted value is 0, you see here your error is very much high. But when your predicted value is 1, your error is very less, or the cost function value is very less. So when you put y predicted is 1, then log 1 is 0. So the actual minus predicted, the cost function is very minimum, so you may get with the less error. Similarly, you can use for case 2. When you put case 2, y is equal to 0. So that time what happened? When the y is equal to 0, the first term becomes 0. You will have the second term. So 1 minus y into, this becomes 0. 1 minus y into log 1 predicted. So you get a value is log 1 minus y predicted. And here also the predicted value can be 0 or 1. Okay. So this is actually terms. So 0 and 1. So you substitute 0, 0 here. And the y predicted value you are putting 0. Then 1 minus 0 is log 1. So log 1 is 0. So this will leads to less error. You see here when y equal to 0, your predicted value is 0. So that time your cost value is minimum. But when the y predicted value is 1, your cost value is very much high, because you substitute 1 minus 1, that is log 0. Log 0 leads to infinity, so which produce the large error. So this cost function is best suitable for the logistic regression to minimize the error between the actual and the predicted. And in order to learn the global optimum and to minimize the error and to increase the accuracy, the logistic regression using an algorithm called as gradient descent algorithm to update the weights values of the regression line or the regression function. Okay, so this is your cost function. So now the y predicted value will be like this. This means we are getting y is equal to w1 x1 plus w2 x2 up to wn xn plus bias. So this can be represented with w1, w2, wn and x1, x2, xn, because it will be considered as a matrix. So this will be added to the bias. You will get this information. Okay, so this information you pass to your sigmoid function. So this is our sigmoid function. You will get the y predicted value. Okay, so you have to learn, this is actually our global minimum and your cost function may be here or here. So how you make your cost function to learn in every iteration so that your weight get updated, weight and the bias get updated. So your cost function will come and reach the global minimum. So how the gradient descent function is working or the gradient descent algorithm is working. This is the formula for updating the weight and the bias. And here the alpha represents the learning rate and this represent the slope of a function. Suppose you may think that your data is here. Okay. So case 1. The data point is here. Actually your global minimum is here. So you want to reach the cost function from this point to this global. So when you draw a slope and this slope is a negative slope. So when it is a negative slope, what happened? We write the formula, that is the new weight is equal to old weight minus learning rate into negative slope. Okay, so case 1 is negative slope. You are in the left side of the global point, so we want to reach to it. So the slope is a negative slope. So when I do it, what happens? The new weight is old weight plus this and the slope. Okay, so this is a negative slope. So when you do it, what you have to do? The weight has to be increment to reach the global point. Suppose you consider case 2. The case 2 is a positive slope. That is, your cost function is here. You want to reach the global. So when you draw the slope, now the slope is a positive slope. So when you have a positive slope, the new weight is equal to old weight minus learning rate into positive slope. So when it is positive slope, the equation becomes minus infinity into slope. So this time what happened? You have to decrement the weight to reach our global minima. Okay, this is the way how the gradient descent algorithm is working to reach the global minima, to have the error function is, or the cost function or the error value is minimum with the highest accuracy. And this is the way how it will be implemented in the Python coding. So this is our input, that is wx plus b, and now it will be moved to the sigmoid function, and this will be your y predicted value, and this is the cost function we are having with the terms to reduce the cost function in the logistic regression. And now the gradient descent will be calculated. So this will help you to do the weight and bias updation based on the negative or positive slope, that is Wn is equal to W naught minus learning rate into the slope. The slope can be either positive or it can be negative in order to reach the global minimum. So this will be called for every data point during the training process. It will be called your data and along with the sigmoid function. So this I told with the threshold value, your y predicted value is greater than 0.5, it will lead to the label 1. If your y predicted value is less than 0.5, then it will leads to the class label 0, which helps you to do the binary classification problem. And like this, your algorithm is learned with multiple sigmoid curves, and from that which curve having the maximum likelihood, that curve will be selected as a best curve, which used to differentiate your data into two different class labels. And these are the some of the differences between linear and the logistic regression. Linear regression predicts the continuous variable, logistic regression predicts the categorical variable. And here it used the cost function as the least square estimation, and here it is the maximum likelihood estimation. And the important thing, linear is a straight line and logistic regression is the curve, that is your S curve or the sigmoid curve. And here the data not to be linearly dependent with each value, and the equation here is y is equal to b naught plus b1x, and here it will be y is equal to 1 by 1 plus e power minus b naught plus b1x. Okay. I hope now you got a theoretical background of formulating the logistic regression to solve a binary classification problem by deriving an equation from the linear regression. Thank you.